So good morning everyone. So let us continue the yesterday's class. We had some frequencies, corner frequencies and the basic factors. Let us draw the Bode plot. Your log omega. We have 0 dB line, 20 dB, 40 dB and 60 dB, minus 20, minus 40, minus 60. This is magnitude in dB, right? So I think we have drawn the first asymptote. So what's the first asymptote? A straight line with a slope of minus 20 dB per decade passing through 20 log k, that is k equal to 6, which is 15.56 dB at omega equal to 1. So this is how we have the first asymptote. So what's the first when omega equal to 1? So let us consider when omega 1 means. So let us take this as 0.1. It's not 0, it's a 0 dB line. Remember, this is multiplied by 10, that is 1 multiplied by 10 and 10 multiplied by 10, it is 100, right? This is how you have a logarithmic graph. So we started with the first point at omega equal to 1. Omega equal to, this is log omega now, at omega equal to 1, you have some 15.56 dB. Okay. So this is the first corner frequency also. Omega 1 equal to 1 is the first corner frequency. So till that point, the slope of this straight line is minus 20 dB per decade. So I have to draw this line minus 20 dB per decade till the next corner frequency. But here the corner frequency is 1 itself. So I should draw it backward from this 1. So I can take at 0.1, what is the value? What could be the value of the magnitude? So at omega equal to, here I'll write to understand this. When omega equal to 1, your magnitude is minus, 15.56 dB. So at omega equal to 0.1, what could be the value? Right. So here we mentioned this as a minus 20 dB per decade line. So what does it mean? So your slope is decreasing by 20 dB for every decade. So this value must be 35.56 dB, isn't it? So if you multiply with omega with 10, it will be 1, and there should be a decrease in minus 20 dB. So minus 20 plus 35, it is 15.56. And if you take another value when omega equal to 0.01, so what could be the value? It is 55.56 dB. So this is how you should draw the minus 20 dB per decade line. So I can say at point 1, it should be something like 35.56, and assume this is a point, not 1. This could be somewhere here, right? So we extend this point like this. Okay. So this is your, I'll put it in another way. This is your minus 20 dB per decade, right? So it is also, I can say, asymptote 1. Asymptote 1. This is the first straight line slope with minus 20 dB per decade. So we should draw the line till the next corner frequency. Means here the corner frequencies are omega 1 is equal to 1 and omega 2 is equal to 4 here, omega 3 equal to 6. Right? These are the corner frequencies. So till this point we had minus 20 dB per decade line. After that we need to find out the slope of the straight line till the next corner frequency. Means, so next corner frequency would be, let me write it here, 4, and this could be 6, right? No. So what's the next frequency? Next corner frequency 1 to 4. It should be, the slope of the straight line should be minus 20 dB per decade, right? So from the basic factor 1 by 1 plus j omega, when omega equal to omega less than omega 1 is equal to 1, it is a straight line with 0 dB. So earlier it was 0 dB only, but after omega greater than omega 1 is equal to 1, it is a minus 20 dB per decade. So we should add minus 20 dB to the previous slope, that is minus 40 dB. So from this point to first corner frequency to the next corner frequency, the straight line will be minus 40 dB per decade. Right. Now how do you draw 40 dB per decade, minus 40 dB per decade from this corner frequency 1 to 4, right? So if you take the value at omega equal to 1, it should be 15.56, right? So how do you draw from this point to the next point? Next point would be at 10 only, right? So how do you draw a slope with minus 20 dB per decade or minus 40 dB per decade? So we should take the decade value. But here I have only 1 to 4. So that's why first to find out the decade magnitude, then connect those 2 points with scale and draw that line till the next corner frequency. I'll show you how. Now let us take at omega equal to 1. Here I'm making calculations. When omega 1 equal to 1, your magnitude is 15.56 dB. So I should draw, here I'll write when omega, let us take arbitrary value, omega equal to 10. That is, I'm taking the decade value. So what would be the magnitude value with minus 40 dB per decade? Right. So what would be the minus 40 dB per decade? We should add them, right? So 15.56 minus 40 dB. So what's the value? Can anyone tell the value? correction. It is 4. So what's the magnitude? Magnitude would be 24.44 dB per decade with slope of minus 20 dB per decade. So here we will get minus 24.4 dB. So let us find out that 24.44 dB. So this is minus 22 minus 20 dB per 20 minus 20 dB value. So I need 24 means so I should identify the point here. Okay. So all of you use the graph sheet so that you can easily draw these points. Now draw this line. This now, if it is minus 20 dB per decade, it's very easy. From this point, you should add 20 dB to this value. It would be minus 5. Obviously 4 minus 4.44. So minus 4.44 means here itself. So you get a straight line here. But what is happening? It is minus 40 dB. You have more slope. So it would be something like this. Okay. So let us draw this line. Put the scale here, and draw the line, right? Till the next corner frequency. So next corner frequency would be this one. So I am putting it minus 45 degrees. So I can write it as the graph sheet. I'm just giving the realistic values. So it would be okay. So I'm not connecting this line since I should draw this line till the 4 only, right? So I'm putting the value here. So till the next corner frequency. Now, what's the line here? This would be minus 40 dB per decade slope, and this would be the asymptote 2. Right? Now, let us move on to the next calculation. Now, what's the slope of the next asymptote line? Now I have a asymptote with minus 40 dB per decade at omega 2 equal to 4 from this point to 6, 4 to 6. So what is the slope? From 4 to 6, it would be plus 20 dB per decade. So we should add minus 40 dB per decade at omega, let us say omega t equal to 4. It has some value, and at omega equal to 3, it has some value. We should draw a line between 4 and 6. At omega 2 equal to 4, it is minus 40 dB per decade line. So I should add this omega 2 to next corner frequency slope. So what is that? It is 20 dB per decade plus 20 dB per decade value. So what is the slope from 4 to 6? So it should be minus 20 dB per decade. So it's the value. So from this to this, so you should draw a parallel line to this. Okay. So if you draw that line, I'm showing with a parallel line. So it should be, I'll put here. So this corner frequency would be right. So if you want, you can even find out the slope of this. So at omega equal to 4, assume you have some value is the real value that for omega equal to 4, it is minus 12 dB. So here the value is omega equal to 4, it is sorry, let me tell you the real value. I think minus 9 dB. Yeah. So this is minus 9 dB, so at omega equal to 4. Now, how do you find the slope? So if omega 2 equal to 4, your magnitude is, let us say, minus 9. How do you add the minus 20 dB per decade line? So I should draw minus 20 dB per decade line, right? So at omega, let us say arbitrary value is 40. You multiply with 10, 4 with 10, it is 40. So it should be minus 29 dB. So minus 29 dB at 40. So 40 means 10, 20, 30. Let us say it is 40 here. So put a scale from this point to the 40 dB, that is minus 29, right? This is minus 29. So you'll get, you draw this line from this corner frequency to the next corner frequency. So if you draw it, you'll get this. Now, from this 6 to infinity, so we have no other corner frequencies from 6 to infinity. What would be the slope of the straight line? Now let us write this third asymptote. This should be minus 20 dB per decade, and this is your asymptote 3, right? Next one, from 6 to next corner frequency, we don't have any other corner frequencies, so it should be 6 to infinity. So what is the slope? So from 4 to 6, it is minus 40 dB. Now at omega 3 equal to 6, it's a quadratic pole, we should add minus 40 dB per decade. So minus 40 dB per decade. So it would be 60 dB, minus 60 dB per decade. Right? So from this point 6 to infinity it is minus 60 dB per decade. So how do you draw it? So again, take the at this point when omega equal to 6, what is the value? I think it is minus 14 dB. So at this point, this value, this point at 6, it is minus 14. So from 6 to 60, let us say 60, it should be minus 60 dB per decade. So if it is minus 14, let us make the calculation again so that you can easily draw the line. Now at omega 3 equal to 6, our magnitude would be minus 14 dB. So at arbitrary frequency multiplied by 10, what is the magnitude? So with slope minus 60 dB per decade. So that's why we took multiplied by 10. So minus 60 minus 14, it is minus 74 dB. So identify the minus 74 dB 60. So it would be, let us say 80. You have the slope at this point, right? So this would be the 70 dB. Now draw the line from this point to this point. So put some assume this is minus 74 dB. It is sorry. Minus 74 dB. So from this point you can extend this till the infinity. So now this is the third, fourth asymptote minus 60 dB per decade. And this would be the asymptote 4. Okay. So this is approximate plot. I think approximate plot is enough for understanding the concept. So later we'll do the corrections. Let us find out the gain crossover frequency, phase crossover frequency, gain margin and phase margin for this Bode plot. To get this, we need phase plot. So let us draw the phase plot and find out all 4 parameters. Yeah. Right. Is minus 80. So let us draw the phase plot. Log omega. Assume this 0 degree. Take 45 degree span. It would be minus 45. It depends on your values. and we have seen few values for this. Okay, now let us look at the phase angle values. At omega equal to 1, your pi value is minus 123.91. At omega equal to 1, omega equal to 1 means this one. Okay. Since we are taking the same scale, should be 1 here. It is 0.1. It is 10, 100, right? So at omega equal to 1, your value is minus 123.123 means it will be something like this. And then we have at omega equal to 4, let us say 4, 5, 6, and 8. We have few values at 4, 5, 6, and 8. So at 1 it is minus 128. Here I'll write omega equal to, sorry, omega equal to 1. I'll write another way. Omega value, pi value. When it is 1, it is minus 123.9 degrees. At omega equal to 4, it is minus 40.8 degrees. And omega equal to 6, minus 204.2 degrees. And weight, it is minus 226.4. I think it is 140, not 40. It is 140.8 degrees, right? It never go up. So it is minus 140. Make a correction. At omega equal to 4, it is minus 140.8 degrees. Assume this is 123, and at 4, it would be 140. That is here. At 5, 6, it is 204. It's almost here. At 8, that is 226. That is here. Okay. I hope you can see the whiteboard now. I connected my GeoNet. Of course, there is a power problem. So can you see the whiteboard? Can I get some response? Yeah. So let us look at the phase plot. We have some values here. See, this is your phase plot. Now let us find out the gain crossover frequency, phase crossover frequency. How do you find the gain crossover and phase crossover frequency? So by definition, what is omega g? That is gain crossover frequency. So it is defined as the frequency at which the resultant magnitude is 0 dB. So that is the gain crossover frequency. Now where do I get the 0 dB line? Okay. Use this. This is your 0 dB line, right? Write it here. I write it in green color. I'll remove all this. Okay, simply I'll write omega g, right? Gain crossover frequency. So the gain crossover frequency is defined as the frequency at which the magnitude is equal to 1 or 0 dB line. Now what is the phase crossover frequency? So the phase crossover frequency is defined as the frequency at the phase angle of the transfer function or sinusoidal transfer function would be minus 180 degrees. So let us find out the minus 180 degrees. This is minus 180 degrees, and you draw a line from this point and touch this phase plot, right? And this would be the gain crossover frequency. And is I can say omega p, right? Crossover frequency means we should project it on the x-axis, right? So yeah. So since it is on the 0 dB line now, so it is somewhere 1, 2, 3, something like omega g. We'll see that. So this is how you can identify the gain crossover frequency and phase crossover frequency. Then what is gain margin? Gain margin is 0 minus resultant magnitude in dB at omega p. So what is the resultant magnitude in dB at omega p? So let us project this omega p to this line, right? So if you project it on the magnitude plot, you have some value. So this would be gain margin would be minus 12 dB. So here I'm not getting exact values, but if you calculate it, if you project this omega p to the magnitude plot, it would be minus 12 dB. It is touching at minus 12 dB means here somewhere it is touching your value. I can say this is your crossover frequencies. At minus 12 dB, we have 180 degrees. So it would be right. So this is your omega G. Sorry, P. We just project this phase crossover frequency on the magnitude plot. You'll get it will touch at minus 12 dB. So what is the gain margin? So the gain margin is 0 dB minus of minus 12 dB. So it will be 12 dB. This is how you can calculate the gain margin. So here I'll write what is omega G is the gain crossover frequency at 0 dB. Gain crossover frequency at 0 dB. So what is phase crossover frequency? Phase crossover frequency at minus 180 degrees. Okay. What is the gain margin? Gain margin is 0 dB minus the resultant magnitude in dB at omega p. So at omega p, what is the magnitude? It is minus 12 here in this case. Now what is phase margin? So phase margin is pi plus 180 degrees. How do you find the pi value? Right. So pi value would be the extend the gain crossover frequency to the phase plot. Extend this, use another color for this, project this gain crossover frequency on this line. Okay, so it will touch somewhere here. So take this value. So here in this case it is minus 128 degrees. So I'll use that. This is your phase plot. Yeah, this is your minus 128 degrees. So it is touching here minus 128. So what is the phase margin? It is 5 plus 108 degrees. So it is minus 128 plus 180 degrees. So it is 52 degrees. Okay, so let us recollect all the points on the Bode plot. So first point, we should draw some asymptote lines. So we start with the basic factor 6 pi j omega corresponding to the pole at the origin. Its lag magnitude plot is the asymptote 1, a straight line having a slope of minus 20 dB per decade when passing through the point 20 log 6, which is 15.66 dB at omega equal to 1. This will be the resultant plot up to the next corner frequency, that is from here to, from this point to this point. Next one, let us add the asymptote 1 to the plot of the factor 1 by 1 plus j omega. So the corresponding corner frequency is omega 1 is equal to 1 only. So since this factor contributes 0 dB for omega less than or equal to omega equal to 1, the resultant plot up to omega is equal to 1 is same as that of the asymptote 1. For omega greater than omega 1 is equal to 1, this factor contributes minus 20 dB per decade, such that the resultant plot of these two factors is the asymptote 2 of the slope minus 20 dB plus minus 20 dB. It would be minus 40 dB per decade. So this will be the resultant plot from omega 1 to up to the next corner frequency omega 2 is equal to 4. So this one, second one, 1 to 4. This is second one. This is first one. Then let us now add the asymptote 2, the plot of the factor 1 by 1 plus j omega by 4. To the next corner frequency, omega equal to 4. So for omega less than or equal to omega equal to 4, it is 0 dB, and greater than omega 2, it would be plus 20 dB per decade. So asymptote 3, its slope minus 40 dB plus 20 dB. So it is minus 20 dB only. This is the third asymptote. So similarly, we did for the fourth asymptote. So minus 20 dB, and the next basic factor is a quadratic pole. We add the slope for that minus 20 dB, minus 40 dB. It would be minus 60 dB. So this is how we should draw the lines, slope of the all the asymptotes. So next we should draw the phase plot by taking omega values 1, 4, 6 or 8, and you can take any value. So see that you should get minus 180 degrees in the resultant phase. So if you're not getting it, we'll see that the condition. So let us find out all the phase angle values for a given or for arbitrary values of omega and draw the phase plot. So after that, find out the gain crossover frequency, phase crossover frequency, gain margin, phase margin. So what is gain crossover frequency? So it is the frequency at 0 dB line. So this is your omega g. So this is your magnitude plot. So wherever it touches the 0 dB line, that is your gain crossover frequency. So in the phase plot, we should find out the phase crossover frequency. So find out the omega p at minus 180 degrees. So this is your gain crossover, surface crossover frequency. Now project these lines omega g on the phase plot and omega p on the magnitude plot. You will get the gain margin and phase margin. So we extend this omega p on the magnitude line, it touches the magnitude plot and take the corresponding magnitude. So in this case, the corresponding magnitude is minus 12 dB at omega p. At omega p. The corresponding magnitude is minus 12 dB. So the gain margin would be 0 dB minus the resultant magnitude, that is minus 12 dB. So it would be 12 dB. Now project this gain crossover frequency on the phase plot and identify the corresponding phase angle. So in this case, it is minus 180 degrees. So with the phase margin would be pi plus 180 degrees. So it would be 52 degrees. So this is how you can plot the Bode plot for a given function. So if you have any questions, you can ask till this point. So with this, I completed the Bode plot. If you try a few more examples, if you have any questions, you can ask at any point of time. So here I will clearly show you the only values. Yeah. If you have any questions, you can ask. So you'll get approximate values, no problem. If it is plus or minus 10%, it is 118 or 120. So these are the factors. So that is, this is your phase margin, PM, 52 degrees, the difference. The gain margin would be I'm drawing thick line. This is your gain margin. Okay. This is your 0 dB line. And this is your projected magnitude from omega p. And there are 180 degrees. So that's all for today.